Okay. Hi, everybody. We're going to get started. So I'm very excited to introduce Euiwoong today. Euiwoong is a professor at Michigan. Um, he completed his PhD at Carnegie Mellon in 2017, which is how I know him. He received the Edmund Clark Dissertation Award at Carnegie Mellon, and then spent some time as a researcher at Simons, and then did a postdoc at NYU with Sebash Kot. Um, and I think of Ewing as somebody who has been wildly successful across like a very broad range of things in algorithms, more sort of like explicitly combinatorial graphy things and more kind of continuous optimization-y things. And I guess he'll be telling us a little bit about that today.
Yeah, thanks a lot for the introduction. Yeah, so I think this it's a long title, and then what will happen eventually is that I kind of worked on the four directions or problems from like variety of areas, including data science, linear algebra, clustering, and then I kind of like attack those research directions. But then I think I realized actually like there's a common theme of interpreting those things as a complete minimum CSPs, constraint satisfaction problems, even though like those problems were like kind of studied in the different domains. So I think that's the common theme. But then in the first part, I'm gonna look at one specific problem called correlation clustering. We're gonna see some algorithm for this, and then I'm gonna in the second part, I'm gonna like step back and then talk about briefly other problems as well. Okay, so as you can see, so it's like four directions, like 10 papers ish. So it's a lot of authors here. So but then let's for the first part, let me just begin with the correlation clustering. Okay. Okay, so yeah, so let's just directly define the problem. Okay, so it's like very simple combinatorial optimization problem. So input is a complete graph G, where each edges are labeled a plus or minus. Okay, so I'm gonna use a red color to denote plus edges, and then blue color to denote minus edges. And then given such a graph, your job is to partition the vertex set into k parts. The crucial thing is that k is not given as an input. The algorithm can choose its own k. So k can be 1 or like n. That's up to the algorithm. And then what it's trying to minimize is a number of minus edges in the same cluster plus number of plus edges in different clusters. Okay, so the intended meaning is that the plus edges want to have these two endpoints in the same cluster. Okay, so if you violate that, and then if you have them in the different clusters, then you gotta pay 1. And then vice versa, like the minus edges want these two endpoints in different clusters. So if you put them in the same cluster, you gotta pay 1. Okay, so you are just like making a clustering to minimize the number of violations. Okay, so that's a very simple problem. Is the problem definition clear? Cool. Okay, so if you look at this example, then there is a perfect solution like this, because all the intra-cluster edges are plus, and then all the inter-cluster edges are minus. So like the optimal value is 0. In this instance, probably there's no perfect solution, and probably this solution is an optimal solution that has a value 2. So that's a very simple problem. And then, so why did we study this problem? I think as a clustering problem, I think it's a nice thing because it's applicable whenever like the pairwise similarity is available. So if you compare this problem to like more conventional clustering objective, like k-means or k-median, then you don't need the ambient metric space to talk about. And then you don't need to specify k in advance. So that's like one advantage as a clustering problem. And then one kind of cute application is kind of building this entity graph on the web. Okay, so if you go to the internet and there are like many pages of Michael Jordan hosted by different websites, then one can ask the question, okay, so there are like 6 pages. And then, but of course, like some of them like refer to the same person. Okay, so then how do we figure this out? Okay, one way to do it is gonna run kind of the pairwise classifier between each pair of pages. And then do the correlation clustering. So that each cluster like refers to the same person. Yeah, that's like one cute application. Or like if you want more like the worldly or secular like materialistic motivation. So this is my Pauline Nikhil Bansal's Google Scholar page. The paper that introduced the correlation clustering, which was like again like Fox paper in 2002, was like cited like now like more than 1,800 times. So like someone outside theory has cared about this problem. And then even I can attest from my personal experience. So I think so in my career I had the only one like non-theory experience as a summer intern right before my PhD, and then my job there was to improve their correlation clustering algorithm. So I think if you're me, I think correlation clustering is still 100% what's going on in the industry.
Can you tell us what the application was?
application was this guy.
It was finding Michael Jordans.
Yeah, exactly.
So based on the same methodology, you'd say there's one application.
Yeah. Okay, so yeah, but then like the point vector theory, what's the history of this problem? Again, yeah, this problem was formulated 10 years ago by Van Blum and Chawla. Even there, like they already gave a const vector. But then somehow I think people like has tried to give a better and better approximation ratios. I think rightfully so, because like in order to like on the way, I think people have developed like new like the algorithmic ideas that happen to be useful for like other problems as well. So I think yeah, one famous problem in the area, paper in the area is on this paper by Eilen, Charter, Newman, that introduced like this the famous algorithm called the pivot algorithm that we're going to discuss later. Also coming up with some like very like cute analysis framework called the triangle analysis that we'll also mention in the talk. And then yeah, before our result, I think the best approximation factor was like 2.06 by Chawla, Makarichev, Shram, and Yarovslavtsev, which is kind of refinement of this ACN paper in some sense. Okay, and then from the lower bound side, actually, at least we knew that the problem is APX hard. So you can't approximate this paper problem better than like 1.0001. Okay, so then, yeah, there's some sizable gap between upper and lower bounds. Probably more interestingly, on all these previous results are based on this thing called the standard LP that we will see. And then that guy has an integral gap of 2. So if you're just basing results on standard LP, then you can't go below 2. And then, yeah, here's our results for like correlation cluster problems. So we gave a series of papers giving decreasing approximation ratios with increasing set of quarters. So the current best number is a 1.437 plus epsilon approximation in the upcoming paper has like made it FPT1 in time, 2 to the poly epsilon times linear time. And then, yeah, we also like have a like slightly better hardness, 24/23. So now it's kind of reasonable number. So there's still like some gap. I'm going to mention this optimal approximation ratios at the end. But then at least for now, let's me mainly present the 24 version, where at least we got the number, best number. And then of course it has ingredients from like previous versions, like somehow packaged differently. And then at the end, I'm going to mention how to achieve the faster algorithm briefly. Here's a plan. Okay, so then let's at least like let me introduce a standard LP for this problem. Okay, so then it's LP relaxation, and we're going to have variable xij for.
Sorry.
Yes.
So M here is a
number of edges. Oh, okay. Sorry.
Yeah.
Number of plus edges.
number of plus edges.
Yes, yeah, because like that's enough to like describe the input.
So it runs faster if it's like
Sparse.
but it's not symmetric in the sense that it's not the minimum of
I think that
Okay,
I think we can handle this as well, but yeah.
okay.
Yes. Okay, so yeah, I'm gonna have like variables xij for like each pair ij. So intended meaning is that they are supposed to mean the distance. Okay, so xij is supposed to be 0 if ij are together and then 1 otherwise. Okay, so then if you look at one ij and then whether it's satisfied or not, so then it will be unsatisfied if ij is a plus, but then the distance is 1, or if ij is minus, but the distance is 0. And then of course, like the xij, I think one can put triangle inequality constraints as well, because if ij together, jk together, then ik must be together as well. Okay, so then, yeah, based on this is a very simple LP relaxation. Okay, again, the objective function is a summation of all the plus edges, xij, plus summation over all the minus edges, 1 minus xij, according to that observation. And then x, it's just like, yeah, it needs to be a metric between 0 and values. And then that guy has an integrality gap of 2. Okay, so that's a standard LP, and then we go like beyond this. So then at least our like a main kind of conceptual idea was to introduce this LP, which is like strengthening of the standard LP. Okay, so then yeah, apart from like the original xij variables, I'm gonna introduce like 2 to the n variables, z sub s for every subset of s. And then the intended meaning is that okay, z sub s should be 1 if and only if s is exactly 1 cluster in the optimal solution. Okay, not a subset, not a superset, just like exactly 1 cluster in the optimal solution. Okay, so then of course, yeah, let me keep the objective same. And then yeah, we can like put some natural constraints for the z variables. I mean, yeah, this one is just saying that for any vertex I, it belongs to exactly one cluster. Obviously, it's true. And then I think probably more interesting constraint of bridging x and z is this guy. So basically, it's telling me that at least in the integral case, so xij are separated if and only if there's like no cluster containing both I and j. Okay? Or like the xij is together if and only if there is the cluster containing both I and j. Okay, so that's yeah, exactly the formalizing this relationship between x and z. Then you can, it's kind of easy to see that, okay, so if x is coming from those kind of z's, so then x must satisfy the triangle inequality. So I think this is a kind of strengthening of the standard LP. And then yeah, that's exactly our cluster LP. Any questions about this guy? It looks reasonable, right? I mean, okay, I mean, unreasonable in the sense that there are like too many variables that, yeah, we're going to deal with. But then like the definition looks like, yeah, it's strengthening. Yes.
Sorry, is it okay if you explain it again?
Explain.
Explain it again. Sorry.
Yeah, so I think, yeah, so, I mean, yeah, so, yeah, so,
Z is the,
yeah,
so ZS is sorry, can you say that?
yeah, so Z is yeah, so it's LP, the Z sub S is a variable.
Yeah.
And then, yeah, then probably I think, yeah, probably this constraint is more, yeah, the most interesting constraint. So I think, yeah, so Z sub S, yeah, so if Z is exactly coming from the optimal solution, so then, yeah, what this constraint is saying that, okay, so Xij is 1, if and only if like this summation is 0. And then, yeah, this summation is 0 means that there's no optimal cluster that contains both I and j.
Oh.
Yes, I think one kind of picture, that marker.
There is a marker.
Okay. So yeah, if I and j are like this, and then yeah, if this is the optimal cluster, so then yeah, z sub s is 1, which means that this summation will be 1 because like that s is a cluster containing both I and j, so that the xij will be 0. If this was if this was a cluster, then actually there's like no cluster that containing both I and j, so then it's going to be summation will be 0 and then xij will be 1. Yeah, I think it's yeah. Okay, so let's proceed. Okay, so then that's but then it's this gives you like some nice breakpoint that divides the whole like the paper into 2 parts. Okay, so then first part is so of course like this guy is LP with 2 to the n variables. So like naive algorithm is not going to solve it. So we got to design a special algorithm to solve this relaxation. So that's going to be the first part. We approximately solve this LP in reasonable running time. And then the second part is like, okay, assuming that we solve this LP, how we round this guy. Okay, so let's start from the part 1. Now and then in order to part 1, now let's try to interpret this problem as a CSP, because like viewing it as a CSP will give us like some kind of mileage, and then we can just at least like look at these existing tools and then see like what we need more. Okay, so then here's like the CSP part. Okay, so let me just try to interpret correlation clustering as a CSP. Okay, so then my interpretation is as follows. Okay, so each vertex becomes a variable. Okay, so the variables can take a value from this the domain or alphabet, okay, which is like the set of like numbers between 1 and n. Okay, so the n is there because like possibly there can be n clusters, and then one number just corresponds to the ID of a cluster. And then each edge just like becomes a constraint. Okay, so plus edge becomes equal constraint. So if the I and j get the same value, it's a satisfied, or like otherwise it's unsatisfied, then you got to pay 1. Minus edge, like it's a not equal constraint. If it's not equal, you're fine. If it's equal, then you got to pay 1. Okay, so then the goal is to find an assignment to minimize the number of unsatisfied constraints. Okay, so that's because by that's exactly the same problem. We didn't do anything. Okay, so then that's kind of CSP if you like know this constraint satisfaction framework. But then if you compare this interpretation to like more like well-known CSPs like the max cut or like max 3 set, so then you can notice like some kind of good news and bad news. There are some differences. Of course, the good news is that instance is a complete graph. Yeah, that's a lot of structure, probably the maximal structure. That's gonna be very good news for us. And then definitely we're gonna harness some good from there. And then perhaps like one bad news is the alphabet size is n, not just Boolean or like constant size. So that's gonna hurt us. And then third one, it's kind of like you can interpret it as a kind of like minor, but then actually it's kind of huge the difference for us.
I understand why complete graph adds any structure. And if you have a CSP and I tell you, oh, and it's a complete graph, how is that good news? Because many of those edges could be empty constraints, right?
Exactly. So at least you gotta like exclude the empty constraints. But then now if every constraint is like at least non-trivial, meaning that like, at least like there's only at least one unsatisfying string, then I think that gives you some structure.
Okay, but I was assuming, I didn't ask about this, but I was assuming that your algorithm extends to the case where there are weights on the edges.
No.
Oh, it's just the unit weight plus minus.
Yeah. So
But you can have parallel edges?
no, I think then basically it comes down to weighted case or like even the general case. So I think so if you actually I didn't tell you this actually this problem in the if the graph is general, so then it's like long known that this problem is basically equal to multicut. So there's like no constant vector approximation. So that was
There's a what?
there's no constant vector approximation assuming the Unicame's conjecture. So best is log n and then that's probably tight. So this one is only for the complete graph.
And unit weights.
And unit weights.
If I give you arbitrary weights, it's as hard as
Then we are going back to general case. Yeah.
So in fact the original work say of Bonsall, Blum, and
Bonsall, Blum, and Chao, yeah.
that was also just for unit weights.
I think so I mean they and then subsequently within a couple of years I think people studied all possible different versions general
Yes,
graph.
we did a paper on the planar case.
Oh, okay.
And for arbitrary weights and approximations.
I see.
That's a much more structured.
Yeah.
That's much.
Yeah,
structured.
exactly. I think that's another type of structure that one can do. Yeah. So
Okay, interesting. And in the sorry. But in that case, the application was computer vision. There's this thing called, it's a sort of a segmentation problem. But in the application that you looked at, that where in the commercial application, was it a unit weight problem?
yeah, that's no, I don't think so. At least yeah.
Okay.
But then at least like they use the algorithm coming out of like the study of complete graphs.
Okay. They use linear programs.
No, and they use like the pivot algorithm, the Island Newman, like the combinatorial pivot algorithm. Yes. Yeah, so that's a very good point. Yeah, so we are only talking about complete graph with unit weights. Then okay, so at least like the objective function is like minimizing the number of unsatisfied constraints instead of maximizing the number of satisfied constraints. Of course, in terms of exact optimization, these two are exactly equal. But then if you start talking about multiplicative approximation, then I mean, the mean makes things a bit harder. Okay, but then at least like let's just start from the good news, because like the good news is that even if you look at slightly less structure for the dense CSP, which just means that there are like omega n squared instead of like exactly n choose two constraints. Again, unit weights. So then, one can say that every dense back CSP, and there's some caveat because alphabet size used to be constant. So every dense back CSP has a p-test. And then there are three kind of independent the beautiful algorithmic ideas that all achieve p-test separately. I think the first one is a complex hierarchy. Second one is called the random sampling. Third is a via regularity lemma. In the talk, I'm gonna briefly at least mention first and second. And then you're going to see how it's going to help us for correlation clustering as well. Okay, so then let's just take a slight detour and then let me just tell you how to achieve the max CSP p-test in a dense instance using the convex hierarchy at least Cheryl items. Okay, suppose that just for concreteness, suppose that we are solving the max cut in a graph with the omega n square edges. And then I'm not going to formally define the Cheryl items, but then it's basically what it is. So for any set of R vertices S, and then for any possible assignment alpha to the S, so I'm gonna have a variable called x sub S alpha, which is supposed to mean the probability that S gets alpha in the distribution of optimal solutions. Okay, so that's the intended meaning of the shell items. And then of course, if you have that interpretation, then one can add more like constraints, ensuring consistency with local distributions. So then, so here's that's the relaxation. And then typically the way people round it is there is probably the only one like generic way to round it, which is like this guy. So you sample like some like seed vertices, set T with the at most R minus 1 vertices, and then you sample alpha from T's local distribution, which you can because we specify the local distribution up to like R variables. And then for the remaining variables I, we independently sample I's value conditioned on the fact that the seed got alpha. We can still do this because like we are only using the local distribution for like T union I, which is still like R variables. Okay, so that's probably the only way people round these things. And then using this the variance reduction lemma that was proved around like 10 years ago, then one can say that value of this rounding, very simple rounding, is almost equal to the value given by the LP up to epsilon times n square at the derivator. Okay, so when epsilon is a 1 over square to R. Okay, so then at least by making R large enough constant, you can like make epsilon small enough constant. So if you look at the max cut with the omega n square edges, then you know that at least for the max cut, so then the optimal value is at least omega n square. So then if you bring down epsilon small enough constant, then that can be like turned into like a multiplicative approximation, at least for the max objective. Yes.
Can I ask something kind of like naive about this that I never understand, which is like, if R is just like a really large constant and like all I'm doing is just conditioning on sort of where I'm placing like 100 of my vertices. Why should I expect then that independently rounding all the other vertices only conditioning on like 100 vertices should give me basically?
So I think idea is that you look at one kind of intuition for the proof is that so you look at the average correlation of the pair. So you suppose that you would sample like random I and J and then see like how they are correlated in the LP. So if they are like not correlated at all, so the independent rounding is exactly like matching LP, so you're good. But then if the IJs are correlated in on average, then what these guys are saying is okay. So then if things are correlated, then if I just sample like one random vertex and the condition of that vertex, so then that's gonna reduce like the variance of all the other vertices. It's like that's what having the large the average correlation means. So so kind of sum of the variances is kind of the potential. And then what they are saying is, okay, so if the potential is like greater than epsilon times n, then one can condition one more, it's going to reduce like, that's kind of the, basically the proof.
Yeah, but can I?
Yeah, sure.
So going back to BRS 11, I think they were, their sample process was influenced by that, right? They were picking that sample based on these correlations. And this was in the context of having semi-definite constraints as well.
Yes. I think PRs I think does like a bit more interesting thing. I think I think this interpretation I think was like I took it from the later paper.
Okay.
That kind of like explaining the things.
Who was that one?
It's the Raghavendra and Tang. I think
Raghavendra Tang.
They use the more like information theoretic language and then yes.
I have like one other silly question, I guess, which is like, what's the formal definition of a dense CSP here? Like, why can't I just have spurious constraints to my CSP that are like P or not P?
So I think because like the way we use the density here is that the optimal value is at least omega n square.
Yeah.
So I think that
Okay.
So of course that then depends on what kind of a garbage constraint you pick. So you put
But I should think of density as like how opt relates to the number of constraints.
At least in this case, that's all they are using. Yes. Good. So that's Charlotte's thing. And then of course, but then if you're doing a mean objective function, then any derivator, like forget about epsilon times n square, like derivator 1 might kill you because if opt is 0, then I want the perfect solution in order to get like multiplicative approximation for the mean. So we gotta handle that. But then how do we do it? It's kind of black box. I don't want to open it. And the way we did it is to do some like combinatorial pre-processing called pre-clustering. Just like the basic idea is like it's essentially very simple. Let's partially solve the easy part of the problem first. So that if you apply this like the heavy black box using hierarchies, then actually we are only applying this rounding for like say like order opt pairs. And then hope is that okay, so if you only apply this rounding for order opt pairs, then probably additive error will become epsilon times opt. And then I mean as I decrease epsilon, then it's gonna be like manageable for us. In particular, if opt is 0, then yeah, then what I want is okay, I want my pre-clustering to exactly solve the problem. And that's exactly what we did. Okay, so we show that there's a simple combinatorial routine that can partition like all the pairs into like E same, E different, E question mark, so that there exists a near optimal clustering such that that's consistent with what we decided. And then most importantly, the number of question marks is at most order opt. Okay, so I'm not gonna show you the proof, but it's kind of 2 pages of natural combinatorial algorithm argument. Actually, one company experience for me was that okay, so it's based on like parallel algorithms for correlation clustering with a large constant approximation. Okay, so again, if you're like a person like me, only interested in like getting a best approximation factor, then I wouldn't typically care about this like parallel algorithms with the worst approximation. But then the ideas from like this work actually kind of was useful for pre-clustering that helped me like get a better approximation ratio among all polytype algorithms. So that was like really cool experience for me.
Can any of this theorem be extended or something to the sparse case?
Sparse, yeah, we haven't thought much about it yet. Yeah, at least like the current arguments like use this the complete assumption heavily, but yeah.
Or even does it suggest a heuristic method that would work for the sparse case to achieve something similar? I mean, is there a plausible algorithm suggested by your theorem?
Yeah, I mean, yes, this algorithm I think itself is quite like quite simple. So yeah, I think that idea might be useful for practice. I mean, actually, like Vincent actually told me that actually their algorithm actually works better in practice than like the fancy approximation algorithms.
Yeah. Okay.
But yeah, depends on how you trust them. Okay, so that's that's a pre-clustering. So pre-clustering is done, and then okay, let me like at least try to tell you what our like, actual relaxation is, because like our goal is to try to solve a relaxation, but then we gotta start from like some like first or real relaxation. And then as you can expect we kind of designed some Shell Adams like inspired relaxation. Okay, so yeah, let's again like fix a constant R. And then let's say like S1 through SL are disjoint sets, some whose union size is most R as usual. And then on top of that, I'm gonna have like the L numbers, S1 prime through SL prime. So yeah, given all these guys, so then I'm gonna create a variable, this funny looking variable called Y sub S1 prime bar S2 S2 prime bar like all the way through. So intended meaning is that let's look at the picture. Okay, suppose that this is optimal clustering. Suppose that this is the set I'm looking at as A, B, C, D. So you can see that the optimal clustering partitions S into 3 parts, right? A, B, and C, D. And then okay, then what does the number mean? Okay, so then one case is okay, A is in a separate cluster, but then if you look at the whole cluster containing A, that guy is like the 2 vertices total, you counting outside S as well. And then yeah, B is the cluster within its own cluster among S, but then it is contain a cluster of size 2 total. And then CD is in a cluster of size 4. So then yeah, here the right variable that should be 1 is like the Y over A2, B2, and CD4. Okay, that's our intended meaning. So it's I mean, yeah, it's I mean it's a Shell Adams inspired. And then yeah, it's intended meaning, and then of course yeah, if you have this interpretation, then you can put all the consistent constraints. And then the crucial part is okay, so of course we did the pre-clustering in advance. So then we are like hard coding decisions made by the pre-clustering into the relaxation.
You're saying the pre-clustering happens pre the relaxation,
yes,
right?
Yes.
First you hard code, you commit to those.
Yeah. So if the pre-clustering says that they are different, so then yeah, we are like just putting the distance 1. There's like no chance that you guys you put these 2 vertices into same cluster. Probably 0. Okay, so yeah, that's our relaxation. And then after doing this, then actually we are rounding. We have to round this our relaxation to solve the cluster LP. And then the way we do this is very simple. So it's kind of iterative. So like in each iteration, we are just sampling one cluster. And then, but then, yeah, we're gonna like find we're gonna like engineer the distribution, so that at the end of the day, like each vertex is containing basically the same number of clusters. Okay, so in each iteration, the probability of vertex sample is the same. So then, yeah, all you're doing is okay, sample all these clusters, and then at the end, take add all the indicator vectors, and then divide it by common number. Okay, that's the cluster LP solution because like basically the only constraint for the cluster LP is that each vertex is contained in one fractional cluster. Okay, so that's yeah, that's at least how we solve it. Then of course, like then problem becomes okay, what you do in one iteration. Okay, so then yeah, then all you gotta do is like sample one cluster from the right distribution, like hypothetical cluster LP distribution. And then I kind of liked it a lot because yeah, now it becomes a 0-1 problem for me. Now I think correlation clustering was kind of more complicated because the alphabet size was n. There are like n clusters. But then if you just like go into this yeah, then yeah, we are now just like 0-1 problem, just like max cut. Okay, now I think I'm happy.
Now, how did that happen? Why is it that it now becomes a 0-1?
Yeah, because like yeah, because like if now all you're caring about is just like sampling one cluster. Yeah, yeah, from one cluster. That's like the problem of like at least one iteration.
Oh, I see. And you're deciding for each vertex, is it in or not?
Yeah. That yes.
So like what does this random sampling satisfy? That like a vertex ends up in a cluster of size equal to like what your relaxation is telling you it should be in?
Yes. It should to satisfy all this like the natural like what you expect from the cluster LP, our initial relaxation. So then basically okay so then we are almost using the variance reduction rounding that I showed you like for max cut as a black box because like now we can do because even though it's becomes 0-1 problem. So then of course like I'm not showing you all the details, but then one can say okay all the right properties should hold. Okay, so each vertex is sampled with exactly the same number of clusters, and then even if you look at pairwise correlations, okay, so then it's exactly what it should be, plus like this elevator, epsilon times question marks. But then now I think since we ensure that number of question marks is is manageable, it's compared to opt. So then one can show that okay, so the whole thing doesn't lose much, and then we are like solving cluster LP, at least approximately. Yeah, so that's at least the high level idea of solving part. Okay, so then the rounding part, I think actually so I'm gonna I want to get to the second the part of the talk, which is like where I talk about different problems. So I'm gonna be very brief here. Okay, so I think so at least like the rounding algorithm. Rounding algorithm, I think it's at a high level, what we do is okay, so we run two algorithms. The first one is called cluster rounding. Second one is called pivot rounding. We just like run like two rounding algorithms separately and then just take the best solution. That's our entire rounding algorithm. And then as you can see, the algorithms, these two algorithms are like the grand total of about maybe 10 lines. Okay, so the algorithms are extremely simple. Cluster rounding, the analysis is very simple as well. It's like analysis again like 2 lines. And then the analysis for the pivot rounding that is known as a triangle analysis. So that's we follow the standard setup. So I think it's still okay. And then so that's fine. What we do kind of new compared to other work is to kind of amortizing like different types of triangles. Let's try to see how much I can get. Okay, but then cluster rounding. Let's start from there. Okay, all I'm gonna do now is just like show you this is the entire algorithm description from the paper, and then this is the entire proof for that rounding from the paper. You can see that it's so basically 2 lines, Okay, so let me just skip it, because it's not super relevant to like the next part of the talk. But then as you can see, okay, if you stare at it for like 30 more seconds, then you would have figured it out. That's cluster rounding. Yeah, I think very simple, already to approximation. And actually, but then one thing I wanted to mention is that this rounding is specific to the cluster LP. So this rounding algorithm did not exist in the previous the algorithms. Okay, let's go to people. Yes.
Is the 2, or I guess 3-line proof also, does it show that it's a 2 approximation?
Yeah. It's Yeah, so and then that's the pivot algorithm. Again, you don't need to worry about the other stuff. So the pivot rounding is something that has existed for correlation clustering for like 20 years, and then basically the whole idea is that, okay, so again, like we are doing iterative rounding in a sense that we in each iteration, yeah, we are like choosing one cluster, make it one cluster, take it out from the graph, and then just recursive the rest. And then it becomes the problem of like choosing one cluster in each iteration. And then the way people do it is randomly choose a pivot vertex U, and then decide which other vertices will go into the cluster of the pivot. And then of course, then yeah, you can see that even with the standard LP that have a distance information between the vertices. But then yeah, that's kind of useful thing to do. But then because typically you expect that the vertices close to pivot will likely go into the pivots cluster this iteration. Or like if it's far from pivot, then it's gonna like stay put and then like just be considered for next iterations. Okay, so that's the entire idea. Yeah, and then actually this stuff I think we do we do use like some z variables as well, and then we do things differently depending on the plus neighbors and minus neighbors. I think this one is kind of the outcome of fine engineering that I'll say I think of my co-authors. So yeah, we just like chose the right routine to minimize our number. But then anyway, okay, so that's but then it's like this framework has existed for a long time. So now I think it's time to analyze it. And then this analysis framework, I think it's pretty standard as well. So let me just skip it. But then okay, but then the whole point is that okay, so of course it's like it's multiple iterations, but then we can only one can individually look at one iteration, and then even in one iteration. So then if you look at what's going on in one iteration, so then one can write down the relevant expressions in terms of like the summation of three vertices. One coming from the choice of pivot, and then two coming from the summing of all the edges. Okay, so that the both quantities are like summations of like P, U, V. And then this like it's a very simple idea, but then the genius of the pivot analysis is that okay, so if you look at these two expressions, they are like of a similar form. So then if you want to prove the inequality between them, the first thing to do is like term by term analysis, and then sadly it doesn't work. But then somehow the triangle analysis actually the group sum is like the three terms, just triangle by triangle, and then if you do this somehow magically then this claim, one can have this claim saying that for all possible triangles PUV, if you group these three terms in this manner, so then one can prove that the alpha is most alpha times LP. That's how like always like the typical analysis goes. Yes.
Wait, sorry, I missed what alpha was.
Alpha is the approximation ratio. Yeah. So then of course so then if you look at this claim, then it's it's some claim, but then it's now constant size claim because it holds for every triangle, but then each triangle is described by like three signs of the edges and then three LP values. Okay, so it's just constant size claim. You can just prove this like via brute force, and then that finishes the whole analysis. Okay, so of course I'm not showing you much, but then if you just stop this, then at least we got 1.5 approximation. Okay, so that was good. Yes.
Wait, sorry. When you say it's the approximation ratio, is it 1.5 then, or?
And then we did more. So so I promised you 1.437. So then what we did more is that at least for our algorithm, if you just look at the claim, then there is a triangle where like 1.5 is tight, and then that's triangle that has two distances at 1/2 and then last distance is 1. That's kind of like always a bad triangle for like many of these algorithms. Okay, so then if every triangle is bad like this, then 1.5 approximation side. But then our question is like, can it? Okay, so because anyway, again, we are using the fact that we are like looking at the complete graph. So then if you look at the complete graph with the distances on these vertices, and then we're asking the question, can every triangle be like half one triangle? For example, if you look at this triangle, so then the J is an anchor of many bad triangles. So JAB is a bad triangle, JBC is a bad triangle, JAC is a bad triangle. So then can you see like what's the issue about this picture? Yeah, so again, like distance, 1 means that the ABC should be always separate. And the distance half means that they gotta be together with the probability half. Yeah, it doesn't make sense, right? Because like ABC should be always separate. But then how can you make sure that each of ABC should be with J with probably 50%? that shouldn't happen. So that situation cannot arise. And then one kind of fancy way to do is look at this matrix A sub j ik, which is a probability of ijk same cluster, and then one can look at this is a PSE matrix because some kind of covariance matrix. So then we can look at we can add like some PSD constraints on this distribution of triangles. So then at the end, based on this observation, what we do in the paper is, okay, if you just like define triangle types to be the triple of three like distance values, pseudo discretized. So then our question is, given like triangle distributions. So yeah, so if you just tell me that, okay, there are like 10% of triangles of like distance like 0.1, 0.1, 0.2, 20% of like distance 0.3, 0.4, 0.5, then is it possible to have a complete graph whose triangle distribution matches what you give me? Because like clearly there are like some triangle distributions like that don't make sense. And then we still don't know how to solve this problem exactly, but then at least we can have like two STP constraints on P. So then what we did is run this vector living STP that certified that for every the distribution of triangles, at least passing our STP constraints. So then I see the whole triangle distribution, so I can kind of do the average analysis. I can amortize over different triangles. And then if you combine the close surrounding, that's how we squeeze a final number. Yes.
Wait, sorry, what exactly is the PSD constraint that's like ruling out?
So I think this. I didn't say anything about it. Yeah. So basically, this matrix being PSD is the one constraint. For any fix any J and then look at this matrix A sub J. So each of this A sub J matrix should be PSD.
Why should I think that like says something about bad triangles?
Because if you look at the situation where like all the I think there's like some kind of conversion needed from this vector P to this kind of matrix. I forgot the conversion, but let me just discuss how. Okay, so then so that's at least like how we got a 1.437 approximation. And then so then of course like the question is like what's going on with between these two numbers? Actually, another like the lower bound is that actually cluster LP that I showed you. I mean, it's a nice LP, so very strong. But then that guy is a gap of 4/3 already. So there's like it's not very far from 1.43, so it's kind of close. But then of course like can you match this? It's an interesting question. But then even for the standard LP, even though it's not giving you the best approximation vector, the best upper bound is like 2.06, and the best lower bound is 2. So we don't know how to match. So I think perhaps we need kind of more algorithmic ideas to round this LP, probably beyond this like the triangles. And then 24, 23, 20, that hardness is based on like morally like the gap for like cluster STP. So cluster LP like gives you one number to each cluster. I think perhaps one can think about the cluster STP where you give one vector to each cluster. I think, but then question like can you solve it or like can you prove that it's optimal? And then so first open question is okay, what's the approximation factor for this problem? Okay, so that so that's the 1.437 number, and then let me just briefly tell you the ideas go into this like the newer paper that solves the cluster LP faster. So then, of course, then actually our route is totally different. Okay, so I mean we solve the cluster LP by starting from Charlotte items and then rounding Charlotte items. But then the Charlotte items, it's kind of like Burkean, and so I don't know, I don't know a good way to like deal with this, especially if you're going for like faster running time. So then our approach this time was okay. Like I told you that there are like 3 independently beautiful ways to solve dense next CSPs. So now our like way is okay. Let's just try the second way, which is based on random sampling, and then see whether that helps us.
I see. So you're moving away from Charlotte.
I'm moving away from
because there are, as in BRS11, there are techniques to solve to do the rounding. From a Shirley-Adams instance in similar time.
Yes. That one probably could have tried. I think that's still a possibility, but then I think we found it. At least like that different route simpler. I think that's still possible. Okay, so I mean this one I think okay. For the interest of time, like let me not actually that's a whole proof for like for solving dense CSP. But then at least like this, the algorithm is based on like random sampling. Just like, okay, basically what you want to do is you want to sample like some set of variables. I said log n, but then actually it can be made like 1 over epsilon squared. So I sample like some like constantly many variables, and then see then guess their optimal values. You can do it because you only sample constantly many variables, and then use that information to decide the value of all the other variables. Okay, so if your instance is dense, so then like having just the guessing the optimal value of the constantly many variables will already give you like enough information to propagate to like all the other variables. Okay, that's basically what's going on here.
So you're not using a mathematical program at all here?
No, it's just purely combinatorial. Okay, so then yeah, based on this, so then the way we solve cluster LP faster is so yeah, if you remember a cluster LP, and then let's just like take a dual, and then the dual separation problem becomes something like this. So you're given alpha v, like alpha value for each vertex v, and then your job is to find s that minimizes the cost of s divided by the total value of alpha contained in the set. Where like cost of s is basically defined as this quantity, just like the cost of making this guy one cluster. Okay, so the minus edge is inside, and then plus edge is cut, divided by 2 because there is a double counting. Okay, so that's a dual separation problem. But then of course, yeah, you kind of see that it looks like a sparse cut problem. You're like trying to minimize the cut value in some sense, normalized by the total alpha value you contain in the set. Okay, and then of course, like this is a complete graph with 2 types of edges. That's kind of like a sparse cut and a dense graphs, more or less. So then, yeah, I think here, even there, like the random sampling kind of works. And then it's kind of fast. It's a FPT running time, 2 to the 1 epsilon. And then, yeah, so then, yeah, we took this guy, and then, yeah, of course, we can plug our solution to dual separation into like the multiplicative or weight update framework. And then, so if you just plug in, then that's how you solve the cluster really faster without any shell relaxations.
So wait, where is the multiplicative weight used here?
I think I think the way I see multiplicative is like at least the multiplicative rate, the way I imagine is that you kind of maintain the distribution over constraints.
Oh, you're saying it's used to solve the dual separation?
And I think the dual separation is used to implement the
Oh,
multiplicative
okay,
rate.
got it. All right. So instead of doing like an ellipsoid, you use something.
That's another way to look at it. I mean, it's approximate solving, not exactly solving.
Yeah.
But even that requires a dual separation. Okay, so that's the first part. Okay, so then let's go to the second part of the talk where I list like a bunch of other problems that we solve like using kind of this kind of ideas. But then for the interest of time, I think let me just skip all this like the formalisms about mean CSPs. Let me just give you the list of the problems. So this is the first problem that I view as a CSP. Okay, so it's a low rank approximation. Okay, so the input is a matrix A and integer k. Our job is to find the rank K matrix B to minimize some similarity measure between A and B. I think, formally we just looked at the LP, N2 is an LP norm. Okay, so if P is 2, then it's a Frobenius norm. So that can be solved easily. But then, we are looking at different P's. Okay, so that's a well-studied problem. But then the way I view this problem as a CSP is I'm going to create the N plus M variables, 1 for each row and then 1 for each column. So they become variables that can have a value from R to the K. So that's the domain alphabet. Okay, so they're like the vector valued variables. Okay, so of course, now it's very different from just like the 0, 1. Now it's like uncountably many. But then at least one can say that one can imagine that if K is constant, then it's we have some nice linear algebra effects, so it's not going to be too bad. Then you can kind of see that. Okay, so the nice thing about this is that we have many constraints. Because for each row and column, we have a constraint saying that, okay, so the inner product between these two vectors must be exactly equal to Aij. Okay, so the constraint graph is a complete bipartite graph in that sense. Okay, so one can, that's a kind of stretch, but then at least that's one way to interpret the low rank approximation of CSP.
That constraint would hold if there were an answer, a solution of value 0, right? If B were exactly equal to.
Yeah, so I think now I'm kind of making even like of course, like if you look at the LP low rank approximation, then actually then the cost you gotta pay for this entry depends on how far you are from the
Right,
AIJ
right.
value. Yeah. But yeah, again, it's a
For at least for p equals 2, this problem is polynomial time solvable,
yes,
right?
yes, yes.
But for p not equal to 2, it's not. It's
Yeah, exactly. So then that depends on whether you want your running time to be like exponential k or not. So I think so our result is that if whenever k is constant, then for any p, you can get a p-test.
I see. P-test.
Yeah. So it's yeah. But then I think for many of these things, actually, if k is general, then actually you can't expect p-test. There's like some inapproximability.
What's the dependence on k of the p-test?
It's I think this one, I think it's n to the n to
And
the poly k.
yeah,
This one is like this one's bad worse. But then at least this one is n to the poly k, I think.
still bad, but
Yeah, still bad. Yeah.
I mean, yeah, I mean, you could hope for an algorithm with a running time like the one you gave for
Yeah,
for
yeah,
cluster,
yeah,
right?
yeah. I think that's still
An FBT type.
might be
So,
possible, but yeah.
yeah.
Okay, sure. Yeah. So but then one thing I'm gonna say is that at least for this paper, like actually this paper, I think I didn't do much algorithm. I improved the hardness, and then the algorithms were handled by sketching experts. You see, like W as a David Lujoff there.
Mm.
And then one thing I liked is that okay, so the technique they used is this thing called the guess the sketch technique. Of course, like they are sketching experts, so they were doing sketching. But then one thing cool is that okay, so yeah, just like if this is your optimal solution, if you know L, then definitely you can figure out R, and then like propagate back to L. So that's easy. Of course, you don't know L. So then what they do is like let's hit the sketching matrix S on both sides from the left. So then L becomes SL. Then of course, I mean if you kind of believe that solving for SL is enough, so then you're in good shape. Still you don't know SL, but then now the SL is like L times K matrix where like the L is constant, K is constant, so you can guess what SL is, and then that's basically their technique, which is like similar to the random sampling the idea for CSP that I just told you. So I think I kind of found this the similarity very interesting, and that's one reason that I studied this further and further because like it's two different technique. I mean, they're the same technique to study in two different communities. Okay, so I think there are some other problems that we studied. One thing, another thing. Just let me define the problem. It's called the metric violation distance. Now you are given some distance matrix A. Let's even say symmetric, and then your job is to change the minimum number of entries to make it metric. So I think if you look at this example, if you change like 4 to like 1 or 2, then it becomes a metric. The kind of cute problem. And then one can still like interpret it as a complete CSP, where like the alphabet now it's become more abstract, just like points to the metric space. And then but then you still have a complete CSP because now still we have a constraint between every pair. And then we gave a log-n approximation using again like the combinatorial pivot algorithm. You sample like uniform vertex P, and then do something, and then curse with the rest of the instance. Okay, so it's still getting constant factor approximation open. And then there are like some other results. And then inspired by this, actually, we also like went back to like more like CSPs and do kind of classification of CSPs, mean CSPs, so coupling instances. That's still like a very much ongoing work. One cool thing we did is okay. So if you think about even 3-set, that has a constraint for every triple. I mean it was not clear to me whether we can solve it in polytime or not, and then that's what we did in this paper. And then now I think it's we're kind of studying the approximation version of this question. Okay, so that's it. So this is a summary of the problems we studied, and then in Elsa I showed you like two techniques to solve the CSP, which were used for these papers. But then we also needed to do more because like we wanted to handle a mean objective. That's it. Thanks.
I guess big picture. I mean, is there some axiomatized, some theorem, very general theorem or meta theorem that
I think
come out of this? You're recognizing the similarities.
Yes, I mean, I saw like 3 samples so far, and then the eventual goal is to, okay, like let's just develop some like generic theory explain these guys. I mean, including these infinite domains and stuff. Yeah, I don't know. Yeah, it's gonna be possible, but then yeah, that's what I'm thinking.
Okay.
I guess that, yeah, relatedly, I'm curious about, like, you play this trick where you sort of like massage your, at least for correlation clustering, you can massage your instance to the stuff that you sort of like don't know the answer to, has size of like optish, and then you're happy to sort of like pay something additive and sort of like
Yeah.
the remaining cost. Is that like a one-off for correlation clustering, or is there a method for that?
That's like very specific to correlation, I think, and then I've never seen like anything like it.
Yeah.
Yeah. So it's it's a bit like mysterious even to me. What is going on? Can it be generalized? Yeah.
I'll ask you more about that later.
I'm sure there's some examples of approximation out in the broad sense of that idea.
I would think so, but I can't think of anything. But
I mean, you know,
Yeah, I mean, as a like kind of the relaxation like hierarchy purist, I think because like we needed to add this like we need to hard code these constraints into the shell atoms. I don't like that. Then of course like the question is like, yeah, then can you just prove that initial shell atoms has a small gap? That I still don't know how to prove it.
you're saying without doing pre-clustering?
Yeah, without like doing pre-clustering and then hard coding, can you at least show the integrality gap the initial relaxation is small? That yeah.
With a low hierarchy.
Yeah, with constant linear levels.
cool. So, we'll do it again.